All right, welcome back, friends. This is episode 27 of Uncertainty and Probability Theory: The Logic of Science. This is an episode where we're going to catch up a little bit, review some things, and it's kind of a grab bag. I'm doing this mostly off the top of my head. I just jotted down a few notes. For one thing, you see the location has changed. I am there's some repairs undergoing the shack and everything, so I'm stuck with this whiteboard here for a little while, and I don't have the lighting right for it. I have shadows, or I have a light that's too bright, and then it looks ridiculous. We're stuck with this for a little while. I hope you don't mind, at least for a few weeks. All right, so I was reviewing the book. National Association of Scholars asked me to review the book Bernoulli's Fallacy by a guy named Aubrey Clayton, who's on our side on all of this probability thing. And it struck me when I was writing this, and I wrote a review for them, and it'll be out in their academic questions, I think in the spring edition or something, which comes out in January, I believe, that the best way to summarize all this is that probability, there's only two main interpretations of probability. There's lots of sub-interpretations and twists and all this kind of stuff that we've gone over and looked at over these past 6 months or so, but there's really only two. There's the one that I advocate, that probability is in your mind. It is a matter of our thoughts. It is a matter like logic is. Logic is in the mind. Logic is not in the world and causative. Neither is probability in the world and causative. It's a way for us to summarize our thoughts about certain propositions, given other propositions that we assume are true. And that's it. That's just basically it. For this view, we have probability of our proposition, which is just, I'll use the label Y here, and this is our evidence. The evidence can be anything. The evidence could be absolutely anything. I can see the shadow. The proposition is whatever we're interested in, and whatever makes sense to us, and the evidence is at least whatever definitions and grammar and understanding of punctuation and everything that goes into making that proposition sensible. We must never forget that. That's always tacitly there, although we almost never write it down. That's one of the first things we learned a long time ago. But it's there, it's definitely there. And that confusion about that when we don't write that kind of thing down, I've told us about notation many times. Notation can be a help or a hindrance. And in this case, it's a hindrance if we don't remember the grammar and definitions of the words and everything in here, because the chance of equivocation is always here, especially in probability. I'll give you some examples. Now, this evidence could be absolutely anything. It could be observations, data observations. It could be all kinds of mathematical models. It could be just vague thoughts that we're unable to articulate completely, but they're there. You'll hear this kind of thing all the time. I saw a guy on Twitter. He said the probability of the election, and there's implicit evidence, I don't know what he used, some implicit evidence, 60%, 0.60 in favor of Trump. He says, I give it a 60% chance. Okay, well, all right. In other words, he's got some evidence there. We don't know what it is. We don't know if he's properly deduced this number 0.6 from the evidence that he has for this question, but that's neither here nor there. This is what he said. And this is a perfectly valid thing to do. It runs the risk of sounding subjective. We learn subjective probability is one of these interpretations which doesn't work all the time. It doesn't work for very simple. It doesn't work all the time. You can't just substitute it in. There are some definitions. For instance, when you just have simple equations, like we have x plus y, I think I don't remember the exact figure we did, x plus y equals 7, and then y equals 4, and we want the proposition, this is our evidence, and we're interested in the proposition that x equals minus 17. Well, if one of our bits of evidence is the rules of algebra, then we know this answer. We know the probability of this particular thing. We know the probability of this proposition given this evidence. We know that's going to be 0. But if you're a subjective probabilist, you're allowed to say, well, I don't know, these guys might be trying to trick me. So you have not only this evidence, but you have vague, indigestible bits of potatoes in your gut or something like this. And you're allowed to say it's, oh, I don't know, you can say anything you want. You can say it's 0.4. You could say anything absolutely you like. It doesn't seem to follow. So subjective probability, we learn the difference. These premises are subjectively chosen. The proposition is subjectively chosen. I don't really have a big beef with subjective probabilists, except that it's not solely subjective. The only thing that makes the real big difference between logical probability, which is what I'm giving you here, is that once we have written down the evidence, or settled it one way or the other, and we have the proposition, then it's a straight deduction. Just like any logical formula, any logical problem we have, any syllogism, anything like this, any logical argument, then the probability flows from that deductively, not subjectively. And so it's a point to make, but it's not a big point to make. I'm never going to argue with guys who do things like this, not really. Because most of these are not meant to be taken that seriously anyway, so why should we get too excited about them? So we can do all kinds of things with this particular framework. Absolutely every problem in the world fits into this. So I was thinking about this. I didn't see a lot of football, but suppose you're watching a game everybody likes sports. You're watching a game last week, and the quarterback is going back to throw for a pass, and he trips over some clod of grass or something that was churned up during the rest of the game. And he throws the pass as he's tripping over this thing, and the pass goes awry. Intercepted the other side, runs it back just as time runs out, and your favorite team loses. And isn't that terrible? So, but you could argue if he didn't trip, not trip, and everything, all the other bits of evidence that you have, my team wins. My team wins. You could say something like this. You could say, if the guy didn't trip, plus everything else I know about football and my particular, the capabilities of the two teams, what the score was at the time, all this kind of stuff, the probability that your team would have won, that's the better way to write it, my team would have won, is high. This is counterfactual reasoning. Perfectly fine. You can get this in subjective probability, not subjective probability, logical probability. It absolutely works. We make counterfactual reasons, arguments to ourselves all the time. You know, if I wouldn't have had that last cookie last night, you know, I'd be feeling much better this morning, maybe, probably. You know, all these kinds of counterfactual and other evidence, not necessarily counterfactual, but stuff that can't be checked really easily or isn't checked very easily. So for instance, you want to make the bank says a loan, and it's you, the bank, you go into the bank, you want to make a loan, and they look at you and they look like me or something like this, and you look a little shady, and the bank judges this to be low, and so they don't make the loan. So how do they ever know if this is a good model? Well, there are ways, but they'll never check it because they'll never check this particular instance of this model because they're not going to make it a loan. So you'll never check to see whether this was pretty good on it because the loan, I should say, you have to forgive me, I'm just kind of winging a lot of this. The loan repaid, so that they can make you the loan, that's an act, that's just an act. They want to know whether or not you're going to repay the loan. And if they don't make you the loan, then whether or not you repaid is a moot point, but they could still make that judgment. So we can make, none of this stuff, we make these kinds of reasonings all the time, and it all fits very neatly into this logical probability schema. So that's probability is in your mind. Probability is a relation of one proposition to whatever evidence we assume is true. Simple as that. Every single thing we do, or should be doing in science, should be of this form. And it isn't. We're going to discuss all the pitfalls and fallacies and mistakes that are made. For instance, the Bernoulli's fallacy, that book that I mentioned. I can't recommend the book that strongly, and you'll see in the review why not. But anyway, the guy, I agree with him. But well, that's it. Everything fits into this scheme, and it's real easy. Maybe the math is hard and all this kind of stuff in particular formal situations and so forth, but that's neither here nor there. Computers can do that for us, or you can hire some guy like me to figure it out for you. Any of that kind of a thing. So that's the one branch, the one main branch of probability. And Bayes' formula can be useful here. So sometimes people will call themselves Bayesians if they're doing it this way. And they really sort of mean, they could mean either subjective Bayesians or objective Bayesians, and objective Bayesians more like this. But a lot of them, as we'll see, we don't need Bayes' formula, for one thing. We already did that. I did that for you before. It's a very nice thing. There's absolutely nothing wrong with it. We deduced it. That's one of the first mathematical bits we deduced. Perfectly fine to have Bayes' formula. But it's a convenience, but it's not the reason for any particular probability, because all probability can be just like this. When you add new evidence, say you add x, this is x1, and you add x2, well then you just have x1, x2. And there's your new evidence, and you just recalculate your probability. Bayes can be useful for that, or not, depending. Usually is. Or you can add x3, or you can add any level of information that you want. You can just keep adding information. It's still the same schema. This is just everything that you have, or you're assuming is true. And what you're assuming is true doesn't have to be true. So for instance, you're using as evidence, in the last 10 battles, the elves have beaten the orcs. And we have a new battle. And you've constructed yourself this little world over here. We could do this in logic all the time. If I didn't make this into a probability thing and I made it just strict logic, you'd have no problem with it. But some people have problems with this. So I'd say that's high without getting into any kind of numerical things. It doesn't mean that this is true. It doesn't mean that it's true. This isn't true. The guy did trip. So, you know, to say that he didn't trip when we want to calculate the probability doesn't mean anything. It's just we're accepting it as true in this particular equation. That's the beauty of this system. It's completely fluid. It encompasses any bit of uncertainty you ever want to calculate or understand, and it works. Now that's contrasted by the other main interpretation, which of course also has sub-interpretations. And that is that probability is in things. They won't allow themselves really often to write probability of y given x. They'll write it like this more. They will allow some, they have to separate out and make conditional probability something different. They'll just call this the probability. They'll say that y has a probability, that this probability is in nature. It's in nature. It's part of nature somehow or another. And it's a property that y has. And a property that has, and we've demonstrated this before, that must have some sort of causal effect. Well, you can't calculate a probability of something that's unreal, so you can't use counterfactual reasoning and if probability is in things. Counterfactuals don't exist, therefore we shouldn't be able to think about them at all, or we're being highly irrational if we do, if probability is in things. So nobody has ever actually measured probability. What you can measure is you can measure things. I can measure whether or not y is true or false, presumably. I mean, not everything can be measured, but if I can measure it, I can check whether or not that y is true, right? And so if there's only one time what y happens and y is true, for instance, that Trump is the, what's he going to be, the 46th, 47th president? I never remember the exact numbers. Trump will be the 46th president. Well, there's no probability that's making him going to be the president or not the president. It just doesn't exist. There's no force out there in nature. So you have to remember when we were criticizing some of these things, in order to make any sense of this, so what frequentists will do, that's one of the branches, this is one of the branches of this is frequentism. And they say that in order to do this, you have to embed, frequentism doesn't have to be true for probability to adhere in things. Frequentism is just one of the particular interpretations. But in frequentism, you have to embed this in some infinite sequence. And it has to be unique if probability is in things. And that's a problem. You don't know whether to put this into just presidents of the United States, all male presidents versus female presidential races, or any kind of democratic election. If you're trying to make sense of this, it doesn't fit. It just doesn't make any sense to try to fit this particular event into a unique infinite sequence. And so what they'll do is they reject it. They'll say, well, it's only a unique event, and unique events don't have probabilities because they admit, this is what they come around to admitting, it doesn't have a probability because it's only going to be true or false. And so probability can't be a cause of this unique thing. But somehow, when you put it into, embed it into an infinite sequence of events, all of a sudden it does have this property, this causal property. And so, but maybe you can convince people of this. And here's another one. So you're going to negotiate a salary. And I'm just going to make a cartoon equation, and here's all the evidence that we have, or the potential firm has about you. And they may have some model in their mind that comes up looking like a normal distribution. And we did this, remember, was it 2 weeks ago, 3 weeks ago? I'm already losing track here. We discovered that the normal distribution is an approximation to an approximation. It's a perfectly good approximation to an approximation. The calculations are just a lot easier when they're put into this exponential form and all this kind of stuff. I didn't do any of those calculations for us, but exponential forms are in mathematics very easy to work with. It's a lot easier than working with combinatorics, believe me. Unless you have a particular facility or gift for combinatorics. This kind of level of calculus and everything is a real nice thing to use. But it doesn't mean suddenly that salaries have a distribution. So here's where the equivocation comes in. Here's where the equivocation comes in. If you're a frequentist, you have to embed the salaries into an infinite sequence. What salaries? You know, only electrical engineers if you're going for electrical engineering, only white male electrical engineers, or white male and Asian electrical. You're always stuck for exactly what you're trying to say. And where exactly probability is coming in as a cause. But when I say it doesn't have a distribution, I say this. So suppose you get this salary here. Here's the salary that you get on the. This is salary on this axis, greater, and then of course lesser on this thing here. Here's the salary you got. If you say that salaries possess, is part of, is a property of this distribution, then it has to be that future salaries look at this or somehow know about this and all the other past salaries that have happened and somehow issue a corrective action if the next salary offer is out here. Because it's this distribution, it has this distribution, and it has in mind all the past salaries that I have, it has to somehow cause this thing to fit back into this scheme, and all future salaries to fit back into this scheme. Otherwise, it wouldn't have this distribution. And that's absurd. That's just frankly absurd. You're having the future cause past events in order to, or not cause past, it's not causing past events, but it's taking into account somehow these past events and using it to force this current event one way or the other. So how probability can be a cause, nobody has ever articulated. But here's another sense that salary does have a distribution. And here's that problem of equivocation. I'll just histogram here. So in the end, we're going to collect all the salaries that we've had in our particular sequence, whatever we're going to do. It's white male engineers, electrical engineers employed at this firm. And it'll look like this. You know, most of the guys got this salary, the next one was this, and the next one was this. This was the distribution of salaries that existed. So in that sense, salary has a distribution. But in other words, this is just a measurement. This is the measured values of salary. So you can say it has a distribution in this sense. But the danger then is thinking, well, that this must be drawn. They'll say this is drawn from the true distribution in some way. They use words like this. It's drawn from this true distribution in some way. And that's where that cause sneaks back in without them actually thinking about this cause. So that doesn't work. So, okay, maybe I can convince you about that. Maybe this is right. You think, but you could use this. You could still use this distribution as a model for that distribution. The observed distribution you can use as a model. Nothing wrong with that. It's absolutely fine. In fact, that's how you make predictions with all these kinds of things for futures. But if there's no sense using that distribution for stuff that you've observed in the past. None whatsoever. We're going to get into this when we do testing and everything, because this is what we observed in the past. There's no true distribution this is coming from. This is just what it was. And all of these salaries have individual causes. The person who's negotiating the thing with it, in each case, the individual getting the salary, each of their backgrounds, the needs of the company, the changing economy, all this stuff, and everything that goes on and on and on to giving somebody a particular salary. But there's no true distribution driving this stuff. Okay, but maybe I can convince you of that. But sometimes people have a problem. They say, well, what about quantum mechanics? That has to be, because quantum mechanics uses the wave function as part of its probability. All right, so we're going to talk about the probability of a particle being at x. We'll use a location. We could use spin up or spin out or whatever particular thing. We'll use a location being at x. And everything we have about the information about this particular particle in its wave function. And this just turns out to be a function of the wave function. And they'll say because it's a function of a real thing, this wave, I'll say, is real, therefore the probability must be real. But that doesn't follow at all. For instance, here's the probability of a 6 on a die, which has 6 faces, et cetera, everything you know about a die. And that probability, I'll say, is 1/6. This is real. This is real. It's absolutely real. These are real properties of a real physical object, and it's really going to be thrown in a real physical situation. But this is a model of our uncertainty of the 6. And the reason is I could build a device where I know the cause. I could do the same thing, and I did this. I did this for a coin, and I'm working on the one for the die. I have it down, but it still has a little bit of wobble at the end when the thing hits. So I have to work on that. But I can control all. It's just much harder. It's much harder to control all the causes in a die. I don't know where I put the die. It's much harder to control all the causes in a die than it is in a coin. A coin is simple and flat and easy to do. So, but if I know the cause of the probability of a 6 is going to be in the set 0, 1, depending on which I cause it to be a 6 or not. So just because something contains bits about reality doesn't make the probability itself real. It's still just a model. And this turns out to be an excellent model. And I didn't want to talk too much about this, and I'm not going to talk too much about this until we bring up cause. Because, again, if you're doing an experiment, and you're going to do an experiment, same thing. We'll just assume they're something like normal distributions for some of these things. And here's x, and here's the experiment, and this time here's the particle. Your particular particle is right there. You've measured it here. it can't be that the device and the apparatus and all this kind of a thing for the next setup is looking at everything that you've had in the past and is somehow causing it to make sure that we get enough particles in this particular area right here to fulfill this criterion. It just doesn't work that way. There's no looking back and using this and forcing these probabilities. And the reason that people still think that it has causal properties is because of this wave function here. And that's because of a flawed metaphysics. And I'm not going to talk too much about the metaphysics here now. I wanted to save that till we talk about cause. And the idea is we can avoid all this talk of collapse and all this kind of nonsense about quantum mechanics if we change the metaphysics and bring back Aristotelian sort of metaphysics in which entities, every entity, every substance has partly composed of potential and actuality. Now, I'm not going to talk too much about it here, but a waveform is mostly potential. And that has just as much being as actuality does when we measure it into a specific spot. And, well, we'll discuss all that kind of stuff. So like guys like Robert Koons, Ed Fazer, Dave Oderberg, there's a whole bunch of people trying to restore this idea of Aristotelian metaphysics back into cause. And I embrace all of that, as we're going to see when I think it's the next chapter, or maybe we're going to do Jane's next, I think, because I want to do some of those. The queer uses of probability in his chapter 5. So, just again, to summarize, just because you're using bits of reality doesn't make it all of a sudden probability is real. It just doesn't. It doesn't work this way. In fact, this is a function. The function is something to do. There's a constant and there's the square modular, whatever. It doesn't make any difference. It depends on the problem and all this kind of a thing. In this case, it's 1/6 because I have 6 sides. So I'm still using physical properties of it, but it doesn't make the thing physical because we don't know the cause, and we don't know the cause here either. And we don't know the cause because we can prove the cause cannot be local. That doesn't mean the cause doesn't exist. Bell's theorem, if you know about it or heard about it, doesn't mean no cause is there. It means the cause isn't local. And so that means, again, we have to explore a different metaphysics, and that's where we get into different things about, well, we'll get into that when we get into it. I've already hijacked that thing enough, and that's just enough to tease enough people to make them angry if they know if they know more about this. So we're not going to talk about that anymore. I just wanted to review this. The first schema, the probabilities in your mind, works for absolutely everything. Whatever proposition you have, by whatever evidence you're assuming, it works. You might not always be able to calculate it because you pose such a complex situation that the calculations don't work out, but then there's always ways to make mathematical approximations and so forth, as long as you remember that those approximations are, in fact, just mathematical aids, approximations like Markov chain, Monte Carlo, and Gibbs sampling and all this kind of stuff. Those are just useful techniques. They're not giving us any magic. I'm going to go into that stuff in depth. So homework. I don't have any homework on this. I'm gonna maybe I have I'll put up something for you to read. We've already read all this stuff at least once in Jane's and at least 2 or 3 times in Uncertainty. But there's other papers out there and so forth that it might be beneficial for some of you to read. All right, that's it for now. Like I say, pardon the venue change. It's very difficult to read. I know with the light. I'm going to work on that. I'm going to be stuck at this for a little bit, and then we'll get back to the green board. And that's it for now. Thanks very much for listening.